So thank you very much for inviting me here. It's into your living room, so to speak. It's a pleasure, and I'm really happy you guys are here because it's really cold outside, and it's blustery. We finally got a wintry day, and I know it's Friday afternoon, but it means a lot to me that you came, and I'm actually very excited to be here. Because a lot of the things that I think this knowledge integration program stands for are many of the things through my own journey in the last 10, 15 years that I've come to believe as well. So it's nice that there's a like-minded group of people here. So today I'd like to start off with a story that the orchestra conductor, Benjamin Zander, sometimes likes to tell. And it goes like this. It's the 1900s, and there's two salesmen who are sent to Africa to check out and see what kind of market opportunities there are for selling shoes. The first salesman steps off the boat, looks around, runs to the telegraph office, and telegraphs back to Manchester. Situation hopeless, full stop. They don't wear shoes. The second salesman steps off the boat, looks around, runs to the telegram office, and says, glorious opportunity, they don't have any shoes. This story reminds me of something that just happened very recently, actually about 3 weeks ago. I was in Vancouver. One of the largest science conferences in the world just happened in Vancouver. And what was really unique about this is that at this particular meeting, there were almost as many science journalists that were attending as there were actual scientists. In fact, there were so many of them, they threw their own party, which I kind of snuck into. I hate rush. And I gotta say, the press, the journalists, they know how to throw a really good party. It was fun. Except for one thing. If you actually talk to a science journalist about their field, their profession, and what they do, it's incredibly depressing because their field is dying. You talk to them kind of candidly off camera, or not when they're on, and they'll tell you about all the problems. And it's something that's a real problem with any kind of print media, newspapers, magazines, even television. The internet has come along and really disrupted their business model. And because of this, they've lost most of their funding, there's been huge cutbacks, and the first people to get cut, the first people to get fired, are the science journalists. It's not the sports writers or any of those type of people or the weatherman. It's the science journalists. And it's a really bad situation. Most of these people have to go around freelance. They're scrounging, trying to pitch stories to these news publication outlets, and it's affecting their quality. And it's a very tough business to be in right now. And so I felt bad for them. I mean, it's terrible if you're a science journalist right now. But if you're a scientist, it is a glorious opportunity. It is the best time to ever be a scientist and be interested in communication. Because all of the same things that are disrupting the newspaper's business and this publication, this industry, their entire business model is being disrupted, these are the same tools that are letting scientists come in and be able to share and communicate their message. And this is something I've become very interested in because I feel very strongly that scientists, we should be trying to share and communicate our stories, telling people about what we do. That's something very dear to my heart, not only because I think we have a responsibility to the public, but because I think science itself is about to undergo a major revolution. That we're going to have new collaboration techniques and tools that are going to let different disciplines talk to each other. I'm a physicist. I work in one particular area of physics. And to be honest, I don't really understand what other physicists do who are outside of my area. There's just too many barriers to interact. And I think we're getting to the point where the scientists start taking more responsibility about sharing our own stories. We're going to get better at communicating, and that's actually going to help improve how we communicate with each other. And that's going to be what leads to our next set of breakthroughs. So this idea of how do we use these tools and take advantage of this and start to communicate? I've been thinking a lot about this, and for me, it comes back to storytelling. How do we tell our story and get that out there? And to be honest, it's something I've been interested in for my entire life. You could even say that storytelling is in my blood in some sense. You see, my parents, my father, he's a minister. I was a missionary kid, and when I was young, I grew up overseas. I lived in Pakistan and Sri Lanka and traveled around. My father, his brothers, they're all ministers. His father was also a missionary as well, a minister. My grandfather's father was also a minister, and it's sort of a family business. I'm not in that family business anymore, but it's something that I grew up with a great deal. And when I was about, I must have been about 6 months old, we like to parrot our parents and sort of imitate our parents when we're young. And so I did this. My mom came into the room, and I had lined up all of my stuffed animals in a row. And I'd taken a shoebox and set it up almost like a little pulpit where a priest or minister would stand. And I couldn't even talk yet. And I was standing there, and I was preaching at my animals going, oh, blah, 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 oh, blah, 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 blah. I guess that's what my dad sounded like to me. So my mom thought this was adorable. She didn't think it was adorable when a few months later I decided to take those same stuffed animals and baptize them in a bathtub. So I grew up around these storytellers and these people who, like ministers, they're very effective communicators. They're always thinking about how to elicit emotional response, connect with people, build a community. That's what they're driven to do. And I'd watch my dad as he'd prepare a sermon, and he was obsessed with taking an idea and trying to break it down into its simplest form, condense and crystallize until he got down to the very essence of it. And then he could communicate that effectively. And he always did it through the lens of trying to ask the question about who are we and what is our place in the universe? Now, again, I'm not a minister. In fact, I'm not particularly religious myself. But that inspired me, that thought, and that, who are we and what is our place in the universe? That's been a question that's driven me my entire life. I've always wanted to know, who am I? And learn as much as I can about myself. And that's why I went into physics. Because physics provided for me a way to learn more about who I am. It's a way to look at the world and learn the rules of what's going on. So, as a physicist, we try to figure out how things work. So you take this ball, for example, and I throw it in the air, and I catch it. And as it goes up and down, I know, because of Newton and his laws, how far it's going to go, how long it's going to take, and how fast it's going to be as it travels. And when you start to understand how the world works around you, you can then take it, and you can manipulate and control it, and you can build technology, and you gain a great understanding of how things behave. And I always find it amazing that the same force of gravity that lets this ball go up and down is the same force that keeps the Earth in motion around the sun. And it's what keeps galaxies rotating around each other. And to me, that is one of the most incredible things, that just a few simple principles you can use to explain a huge amount of things. And that's what attracted me to physics. And right now I work in a field of, it's called quantum optics. I study quantum mechanics. And I really got into this field because the rules of quantum mechanics, this quantum world, is so different than anything that I'd ever experienced that I just felt compelled to continue studying it. Now, I got a question for you guys here. Has anybody ever taken a physics class? Okay, so a few of you. It's good. Anybody ever taken a quantum mechanics class? Yeah. Oh, yeah. Okay, good. So there's a few people that are in. All right. So, quantum mechanics is very, very different. You always run into just absolutely strange things. So, for example, if I take this ball and I throw it against this wall, maybe I won't do that again. That doesn't sound so solid. Okay. It's supposed to be engineering school. So, if I take this ball and I throw it against the wall, it comes back. Of course, it comes back. If you were to take an atom or some tiny quantum particle, and I would instead of a wall, if I took some kind of barrier and I threw this quantum particle at that, some of the time it would bounce back, but some of the time it would tunnel right through the barrier as if it wasn't there. It would just keep going as if the barrier wasn't there and just go on its merry way. Quantum tunneling. We have nothing like it that we experience in our normal everyday lives. Yet, this thing that seemed really strange, it is what lies at the heart of the laptops that I see out here, all of your BlackBerries, all of our entire semiconductor industry. The reason that you can make those computer chips so tiny are that the little transistors that go 1 and 0, they're using this phenomenon of quantum tunneling to go back and forth to let this happen. It's actually something that, because we learned something in quantum mechanics, this how nature works, that it's led to this entire communications revolution. So I wanted to find out what are the rules about quantum mechanics and how does it work. And it's an amazing place when you start studying quantum mechanics. The quantum world is far more bizarre and astounding than anything I've ever encountered in any kind of science fiction or any kind of literature. It is absolutely stunning. And so I started to want to explain this to other people. I wanted to share with other people quantum mechanics and all these awesome things. And when you do that, you end up sounding like a crazy person. Quantum mechanics is really hard to explain. I remember when I was a few years back, I just started my graduate work, and I visited a friend of mine in Calgary, and I went with her family. We went up to Banff. And on the car trip, her mother started asking me all sorts of questions, very detailed, probing questions about what I did. And I couldn't really answer her. I couldn't explain to her what I did. I went away going, wow, I actually don't really know what I do. I don't really understand what I'm doing. It was a kind of a shattering experience. And so ever since then, I've been trying to think about ways to explain quantum mechanics. And in all fairness, it's not just that scientists are bad communicators. I don't actually think that's the case. I think quantum mechanics is fundamentally one of the most difficult things in the world to explain. It's in its very genetic code of how it's made up, quantum mechanics. It is hard to explain. And I'm going to go through why quantum mechanics is difficult to explain, and then some of the things that I'm trying to do to explain this concept. So we're going to do a bit of quantum mechanics. And the first thing we're going to do is learn about a principle called complementarity. Don't worry, you don't have to remember the name, but we're going to go through that idea. So I need a volunteer, just someone. All right, I'm going to grab you, because if you could just stand up for a second. Sir, what's your name?
Connor.
Connor, all right, I'm Chris, sir. All right, Connor, do you play sports, catch balls, do anything like that? Sure. You've caught a ball, okay. So I've got this technical task. I'd like you to catch this ball for me. All right, let's give him a hand. All right, that's all I needed to do was catch the ball. Thank you. But what you just saw there was something truly remarkable. We take it for granted, but it was an incredible reaction of hand-eye coordination. That's the product of millions of years of evolution that let them catch that ball and react in that way. I think that's pretty remarkable. And it turns out, you might not think about it, but your brain is a pretty good physicist, because in order to catch this ball, it did some pretty complicated calculations. Turns out in physics, if you want to know where a ball goes, or in fact, if you want to know anything about anything, what you have to do is you have to know two things, only two things. You have to know where it is, and how fast it's going, in what direction. What we call position and its velocity. Where it is, where it's going, because then you say, oh, it's here, and it's going in this direction at this speed, then it's going to go here, and then you can trace up this kind of path. This is like a bedrock principle of physics, of what we experience in everyday life. You go down to the quantum world, completely impossible. I'm sorry, Connor, but you wouldn't be able to catch this ball if I threw it to you. In fact, nobody would be able to, because there's this trade-off that's fundamental in quantum mechanics, where you can either know where it is, or you can know how fast it's going, but you can't know both at the same time. It's forbidden. There's something called Heisenberg uncertainties principle. So this leads to a very weird situation, something that we would normally experience, because every day if I throw you this ball, you can catch it, you know where it is and how fast it's going, but for atoms and particles, you can't tell the path that things go. things behave in this very strange way. And so Niels Bohr, he's the guy that really did a lot of the initial thinking about this, one of the founders of quantum mechanics. And he called this complementarity. He said, position and momentum, position and how fast something's going, these are what we call complementary things. You know one, but the more you know about one, the less you have to know about the other. There's always this trade-off. And this idea that you can have two views of something, you can either see it one way or the other, but not both at the same time. It reminds me of this French poem that I'd like to share with you. So, just out of curiosity, anybody here speak French? So there's a few people. Okay, so you're going to look at this poem. If you speak French, and this is going to sound like utter nonsense, because it's a poem that was written in the form of something in the French Revolution, and it's a very detailed, localized poem, and very complex and esoteric. And so I'd like to read this poem to you. And just for full effect, I'd actually like you to close your eyes as you read this, just to absorb the full power of this poem. Even though it's in French, I'm sure you'll get something out of it. It goes, Little Miss Monfit sat on a tuffet, eating some kids and way. Along came a spider, and it sat down beside her, and the frightened Miss Monfit away. So, if any of you have grown up in Canada or North America, you may have heard a little nursery rhyme called Little Miss Muffet, not this very esoteric and strange nonsense French poem. This is actually by a Dutchman, Louis van Rooten, I think is how you pronounce his name. And he has a whole book of these. It's called Mot der Goose Rhymes, which is Mother Goose Rhymes. So, this poem is really interesting. If you give it to someone who's bilingual, if you are reading this poem in French, you cannot hear the English. It's almost impossible to see the English and the French at the same time. You have two experiences of it. You either have an English nursery rhyme, or you have this French poem. These are two complementary views of this thing. Same thing, but you get these two different perspectives. You can either choose to see the French or the English, but you can't do both at the same time. And so this is this idea of complementarity. Now, Niels Bohr, he went on and he was a smart guy and he said a lot of smart things. And one of them was he said that he thought truth and clarity were complementary. In other words, the more you spoke the truth, the less clear it was. And the more clear you spoke something, probably the less truthful you were. And if you've ever read anything that Bohr wrote, you know he always erred on the side of truth. Because it's almost impossible to understand what he was actually trying to say. So, I got thinking about this, and every attempt I've seen that people have tried to take quantum mechanics and they tried to explain it, it comes out kind of garbled. It's a very difficult subject to explain. And the more I thought about this, the more I realized that for me, physics, especially quantum mechanics, is very much like poetry. In fact, I honestly believe that quantum mechanics is a poem that nature has written to us about how the universe works. The only problem is, nature decided to use mathematics as the language instead of English. Now, one of my favorite things to do is I love reading foreign poetry. I love foreign language poets. And it's also one of the most frustrating things that I do. Because I'll read, I don't know the actual language, and so when I go to read a translation of a poem, it's never quite the same. There's always something that's kind of missing. You can see that it's a really good poem, that there's something that's pointing to, but you know in the original language it must just be mind-blowingly beautiful, and the most incredible thing you ever see, and instead you see this kind of reflection of it. In fact, my favorite definition of a poem is that it's something that cannot be translated. Now that's even if you believe you can define what a poem is, but I kind of like that take on it. And that's the same thing that happens with quantum mechanics. The language of quantum mechanics is mathematics. If you really want to understand at the deepest level, what's going on with quantum physics and quantum mechanics, you've got to learn the math. And anytime you try to explain in English kind of what's happening, because we don't have the kind of analogies, you don't have things tunneling through walls and this sort of complementarity. We don't experience that in everyday lives. It's hard to find the right analogies for that. So, what do you actually do? Like, are we stuck? Is this a permanent problem? I don't think so. I think there's a way we can get around this problem, this truth and clarity trade-off. And I think it's that we have to stop thinking about traditional ways of expressing things. I think the arts can solve this problem. You see, the arts, we often think about, art and science, two things over here and one over here, one over here. They don't inform each other, they're very different. And I look at art, and I look at the way art has taken and developed powerful tools to transmit and communicate ideas. You see what a painter does, a poet, they're able to communicate something that's within themselves or express something about what they see. And they can do it in a very concise, compact way. One of my favorite examples is really of a poem by Margaret Atwood that I think captures the nature of love very well, or at least some aspects of love very well. If I were to stand here and tell you about love, we've all experienced love in some form, I would just be here for hours on end, and it would just be a mumbling lecture. But Margaret Atwood, she managed to capture love in just 2 lines. And this poem, it goes, "You fit into me like a hook into an eye, a fish hook, a bare eye." That's love. Or at least one aspect of love. So, it's this idea that a poet can somehow, they're not like, love really isn't about sticking fish hooks in people's eyes. At least I hope not. But it's using that idea to convey this, the passion of love, the pain of love, going into these things, it somehow transmits that and just is able to really leave you an impression of that feeling. And so I began to think about, the arts and how artists have actually taken and developed all these wonderful ways of communicating ideas. There's this interesting painting that I quite like, Dora Maar Oshab. This is a Picasso painting. And I didn't really appreciate Picasso until I took a physics class on relativity and learned about Einstein's thought on how the universe is structured. You see, this painting here, you're seeing many different perspectives of the same person simultaneously. You're not just seeing a normal portrait, but you're seeing the sides and all sorts of angles. It's a very fractured view, but in yet some way a more complete view too, because you're seeing signs that you normally wouldn't see or experience. And what's interesting is we look around at how we experience life here, but if we were to take and put all of us onto a rocket ship and accelerate us to nearly the speed of light, it turns out space and time start curving and warping around each other. And actually, the viewpoint that you would get of looking at other things will be much closer to what Picasso's showing. You'd actually start seeing almost around corners and seeing the other sides of things. And it's no mystery, or it's no, I think, coincidence that some of Picasso's ideas came about just a few years after Einstein came up with these theories of relativity. I think there's an informative process that goes on and forth. And I think this is one of the best representations of what relativity is. I think it's a beautiful one. So, for me, my artistic side, the kind of thing that I've engaged in, is dance. When I was a grad student, I discovered a dance called the Lindy Hop. Has anybody ever heard of Lindy Hop or swing dancing? All right, there's a few people. Okay, good. I was speaking at a high school a few weeks ago, and I asked that question. There's 600 kids, and up until that point, 600 high schoolers, they're pretty talkative, and there's a lot of excitement. I asked them if they'd seen the Lindy Hop. Dead silence for about 15 seconds. So I had to do a little demo. That was Luckily, one of their teachers was a swing dancer, so I can't do a demo here today. But what I really, so I guess I should tell you what Lindy Hop is. So Lindy Hop is the swing dance that people did in the 1930s. It was the street dance. It was all the cool kids did. And very active, very energetic, done to the kind of big band sounds that sounds like right around Christmas time, the music that you hear a lot. That's the kind of music. It's the dance where usually the guy throws the girl over his head and they do flips and stuff like that. That's what I do. It's a lot of fun. And for me, dancing, I really connected to it in a very deep way. I remember the first time I saw a couple doing this Lindy Hop, the swing dance, I felt like there was a piece of me that had been missing that just slotted in. And I was like, I think I found part of my place in this world. This is incredible. And it was so different than anything I'd ever been doing in physics. And yet, I knew that this was another way that I could learn about who I am and learn about myself. And in fact, in studying physics and in doing dance for the last 7 years, I've learned just as much, if not more, about who I am through dance as I have through physics. But for all of this time, for most of this time, these have been two separate paths. They're separate, almost silos. You know, my dancing is kind of over here, the physics is over here, and you know, the never shall the two ever cross or meet. And this is kind of, it bothered me, but I figured that's the way the world was. You had to keep your life very compartmentalized. And then something really interesting happened. There was a contest that was run by Science magazine called Dance Your PhD. And when I saw that, I was like, if there was ever anything that was designed for me, this is it. So I got so excited. I spent a year, I got some friends together and we choreographed this dance routine. And I was so excited about it. We put a lot of work into it and we did this dance. And it was one of the most rewarding things was I showed it to my mom. Now, up until this point, I had been trying over and over to explain to my mom what it is I did in the lab. And my mom, she doesn't have a strong science background, neither does my dad. They didn't get it. They get blank stares. I remember one time I was really excited. I told them, I got my master's degree, and they asked me, what did you do it on? And I told them, and it was on something called quantum process tomography. My sister, her face just dropped. And she looked at me in horror and said, you're doing it on quantum pornography? So this is like the level of, I don't do any kind of quantum pornography. It's all PG. But I promise. So this is the kind of response that I would normally get from my family. And so I showed my mom this video. And my mom, she watched it. She enjoyed it. And afterwards, she went away, and she went away, and she came back to me, and she asked me a question about what I did. And it was a very good, deep question. It was the type of question that you can only ask if you actually understand something about what you're asking about. And I couldn't believe that she was actually engaging with me in my research like this. It was mind-blowing. Now, it's one thing for your mom to like what you do. It's a totally another thing for your colleagues. And I was really worried at how other physicists who are sometimes quite dour and serious, how they were going to react to this kind of almost frivolous dance. They loved it. I started getting more emails from other physicists in my field who were excited about this and sharing it with their friends and saying, this is kind of what we do, and here's a dance that describes it. I got a better reaction actually from the physicists than I did from most other people. And I realized that there was this huge need for using more creative ways to try and express science. And so that's when it began to dawn on me for myself that if you look at art and science, they can be separate, but there's an area of overlap between them. And I think when we live in this overlap, that's when truly remarkable things can happen. Steve Jobs would probably call that area magical and revolutionary. And different people have explored that. But that's the space that I want to live in. And I think that's the space that you guys are living in here with KI. Like, that's my impression. You have this fantastic balance between the arts and the sciences. And whenever you start to look in that space, that's where the real breakthroughs happen. That's where ideas start to travel back and forth. And since I've started to move into the space with myself, it's helped my physics research, actually. It's helped me understand the world better. It's helped me do better work. It's helped me explain this work better. And it's been completely transformational. Now, I'd like to just go through in the few minutes I have left a couple of examples of things that have happened. So, not long after this Dance Your PhD, I put on a show when I was at U of T as a grad student. It was called The Quantum Physics of Harry Potter. It's online if you want to watch it. So, I was planning this out, and I was having it was kind of a standard talk, but I was having a really hard time explaining this concept of quantum entanglement, what I do in the lab. And I couldn't find a good way to explain it. And I spent literally months trying to work it out. And then I went out with my wife. We went out for dinner with one of her friends, who just happens to be a magician. And it was one of the most amazing dinners I've ever been to. He was there, and he's like, you know what, I like to do tricks. I'll do a trick anytime, anywhere, for anyone. I said, well, can you do a trick now? Suddenly, 4 decks of cards come out, all these sponge balls, dice, and coins, and it was just like this whole magic show for 2.5 hours at the table. And I was like, hey, this is awesome. So he said, you know what, would you like me to come and perform at your quantum physics and Harry Potter show? Now, I've learned in life, if the magician ever comes and says, do you want me to come perform for you? There's only one answer, and that's yes, please come. So we began to talk, and I was like, you know what, I'm just going to run this by you. I've got this thing with quantum entanglement, and I don't know how to get across the core essence. And he's like, well, can you explain it to me in a card trick? So I thought about it, and I said, yes, here's what you need to do in a card trick. So I explained it to him, I said, but this is clearly impossible. And he said, nope, I'm a magician, I can do that. So he came and performed this, and it went over really, really well. And in fact, I'd like to show you a little video of this quantum entanglement, just a short, little 3-minute clip from this. So hopefully this works. Sorry, I'm going to look really fat here. It's not that I put on weight. It's just the aspect ratio of the screen. Oops. Media.
When two objects are entangled with one another, they share a peculiar connection. For example, if I were to take these two molecules and entangle them with one another, I could then take them to opposite ends of the universe, and yet they'd still be connected. Anything I did to this molecule would instantaneously affect this one. Einstein so disliked this concept, he termed it spooky action at a distance.
Nein, ich mag diese spukhafte Fernwirkung nicht. Nein, nein, nein!
Entanglement was the subject of some of the most vigorous debates between Einstein and Niels Bohr, and has played a important role in the foundations of quantum mechanics. But what's entanglement good for? Well, using entanglement, two people can share secret messages between them. Or you can use entanglement to build a super fast computer capable of solving problems that today's machines can't handle. In fact, you can even use entanglement to teleport the information stored in a quantum system from one place to another. Pretend for a moment that I'm an atom. Then using entanglement, I could teleport the quantum information stored within me from here to here,
or here. Quantum entanglement is so strange, it's almost magical. And here to help explain quantum entanglement is special quantum magician Dan Trotter.
Thanks, Krister. Using this deck of quantum cards, Jamie and Krister will help me demonstrate the idea of quantum entanglement. First, I'll mix the cards, and then I'll have each of them mix the cards as well. But first, Jamie, please cut off about half of the cards, and then deal those into 2 piles. 1 pile for Krister, 1 pile for yourself. This mixing process right now is just, in a sense, the type of shuffle, mixing into 2 different piles. Now that you each have your own piles, you'll mix them independently. You'll deal as many cards as you like face down. Whenever you like, you can stop. Then you take everything in your hands, turn it over, lay it back down. Pick it up, and then do that again as many times as you like. Go ahead. Face down, good. Fantastic. And you'll know that they're making independent decisions. Sometimes Jamie's just dealing a few, sometimes she's dealing more before she turns over. Same with Krista. Also note, Jamie stopped already.
I'm not good with cards.
Krista continues to shuffle. Independent decisions. In fact, you could take these two different decks of cards, take them across the universe, and yet, because they're entangled, something very mysterious will happen. You would think that because of those independent choices and shuffling procedures, they would have random orders. When in fact, if we look at the top card of Krister's pile, it's a black 6. The top card of Jamie's pile is also a black 6. Maybe a coincidence. Let's try it. Top card of Krister's is a red jack. Red jack. Red 10. Red 10. 5s, 9s, 8s, 3s, 8s, 3s, aces, and queens. Because they're quantumly entangled, they have a mysterious correlation. And that is quantum entanglement.
Oops, we don't want to see that again. Okay. So that's the trick that Dan did. And that's the idea that I was struggling so hard to explain, was that you could have two objects that have this strange connection, these strange correlations. You have to think about it as one object. And what's even crazier is, as strong as strange and weird and magical as those kind of card correlations look, what I do in the lab with light and little particles of light called photons, I can create correlations that are even stronger than anything that Dan could ever do. And so, what I actually do in my lab is I try to create these particles that have these crazy strong correlations. I think about it as almost like the particles have fallen in love and become entangled with one another. And what I try to do is use these to think about what kind of new technologies can you build? What kind of new things can we develop? And one of the things that you can do is build a super fast computer based on quantum mechanics, what we call a quantum computer. And this computer is capable of solving certain things exponentially faster. So one of the problems that we deal with, that's a very hard problem for a regular computer to deal with, is factoring. So if I ask you guys what's the factors of, say, 15? 3 and 5. 3 and 5. So 3 times 5 equals 15. If you take 21, it's 7 times 3. So it's two numbers that you multiply together, like another number, or the numbers you multiply together to get some other number. So this idea of finding the factors of a number, like 15 is 5 and 3, 21, 7 and 3, this actually seems like a fairly easy problem. It's something you learn usually in elementary school and then promptly forget. But it turns out it's one of the hardest problems to actually solve. If I were to give you, instead of a simple number like 21, if I were to start on this end of the board and just keep writing back and forth and write like a 1,000-digit number and ask you to find the factors of it, it would take you all the computers in the world today, longer than the age of the universe, and you still wouldn't find the answer. That's a hard problem. Turns out with a quantum computer, you can solve this thing exponentially faster, and you could do it with a similar system in about a day, which is a pretty big improvement in speed. So I'd like to just explain in another way this kind of power of exponential, what we call exponential growth. And exponential growth shows up all over the place in many different things. So I've got here this kind of chessboard or checkerboard, if you guys can see it. And we can play a little game where I'm just going to take these like little Smarties, and what I'm going to do is just put 1 on the first square, and I'm just going to keep doubling for each square. So this one gets 2. For this guy right here, I can put down 4, and we can keep playing this game. Like I'll put 8 here, 16, 32, 64, and so on. Now, we'd be here for a very long time if I decided to fill this board out. The reason being, does anybody have any kind of idea how many Smarties I need to put on this last square? 263?
Give me 260.
And how big is that number?
Big.
Very big. It is so big, you would need not just a jar of Smarties, you needed a bowl of Smarties the size of the planet Earth, with nothing but Smarties in it, just to put on that last square. That's how fast exponentials grow. And that's why a computer that's based on quantum mechanics, based on these particles that are entangled with one another, is so powerful, because all you have to do is take one particle, and so in a regular computer, you have things called a transistor that go 1 and 0. We talked a little about that with this quantum tunneling. But in quantum mechanics, you can have something that's both kind of like a 1 and 0 at the same time. And then when it's entangled, it starts looking at many more possibilities simultaneously. So if I just take one of these extra quantum transistors and add it to my computer, I actually double the power of my computer. And that's what makes these things so incredibly useful for solving certain types of problems. So I'd like to end with just a quick little preview of what I'm going to be doing at TEDx Waterloo. I've been involved with a fairly large project. My talk started out pretty small and is now growing to involve many, many people. And how many people, is anybody here going to TEDx Waterloo? Oh, fantastic. So you guys are going to get a sneak peek of what I'm actually going to do in the day. So that talk I'm going to be using some of these ideas, and Dan will be there, and we'll be explaining how you can build a quantum computer. And the more I thought about it, the more I thought that another really good way to explain this is through Lindy Hop, is through swing it. So I got 8 or 9 other friends, and we put together this dance routine. We're going to be doing it to a live band, and it's going to be this whole kind of dog and pony show. It's going to be fantastic. And the routine actually does go through and illustrate all the steps of quantum computing, but from a different perspective. But I was really stuck, and I couldn't figure out how to choreograph exponential growth with dancers. Like, you can't just suddenly start multiplying dancers. So we thought about this, we thought about this, we thought about it, and one of the dancers came up with a really brilliant and artistic and bold plan that has actually changed how I think about some of the things that I do in terms of science communication and outreach. And he said, why don't we get people from all around the world to film themselves doing the same routine as us, like the ending part, and then we can show those videos at the same time. And I thought, oh my God, we only have a month. Like, how are we going to get anybody to learn a fairly substantial part of a routine, film it, and then submit it to us? But my friends convinced me that we should try this. So we got the band together, they recorded the song for us, we put it out on the internet, and we called it Project Q, Q for Quantum. And within a month, this Lindy Hop swing dance community has blown me away. Whereas I thought we'd get maybe 4 cities involved, at last count, we have 36 cities and almost 500 people who have participated in this project from around the world. And it's absolutely blown me away. And people are really excited about it. Because I went out and now have people who are actively trying to participate, something that's the internet's enabled. And so all I did was put it on Facebook and create a webpage, and it just sort of went nuts. It really showed me that to kind of take this engagement to the next level, you really have to bring other people into it. You have to start getting people involved and excited. And so right now I'd like to just end with something that this has just humbled me, how the kind of response, and it's quite exciting when you see the full thing. These will be synced up with the band and with the dancers in the actual routine, which is a whole other ball of wax trying to get the technical requirements done. But I'd like to just show you this video that we put together. And this is a rough cut. You guys are the first people to see this. Not even the other dancers in the routine have seen it yet. I just finished it this morning. So down to the wire. In fact, it's not even finished yet, but this will give you guys kind of an idea of what it. All right, so let's come questions, I'd be more than happy to, about anything, I'd be happy to chat. If you don't, I'd be happy to make my hands more too.
When in your studies did you figure out that physics was really something you loved and wanted to do more? Like, was it in high school or was it when you were in your undergrad?
So there's been a series of steps that this has happened. Like, I can remember the moment where I wanted to go into quantum mechanics, but I remember very clearly the moment I wanted to go into physics. And it was, well, there was literally, I was sitting in class, and I was an 11th grade student, first physics class I'd ever taken. I didn't really know what I wanted to do. At that point, I thought I was actually going to go into and become like an English major. And I was sitting there in this physics class. First few weeks were kind of boring. I didn't really engage that much. And then our prof, we started something called projectile motion. It's just, calculating, you throw things up, where do they land? Blew me away. It was like, just something clicked, and I understood for the first time. I'd watched baseball, I'd watched cricket, I'd watched football, I'd watched basketball, I'd watched all these sports. I'd engaged with the world, just that kind of happened. But for the first time, I understood that things just didn't happen, but you could actually understand why they happened. That there was rules that governed what made this go on. And when I realized that, it completely opened me up to a whole new possibility. I understand what physics was. I realized, I was like, I have to figure out what's actually going on. I have to learn more about the world around me. And for the rest of the year, I ran around with a calculator, calculating everything I could. I'd be like, how long will this take to drop into the toilet? And just things like that. And so, very, very exciting. That's one moment.
When you're trying to explain really jargon-heavy things to people who don't like it, do you have any, ways you decide when to teach someone a term? Like, is there do you never use jargon, or maybe use one or two tasteful pieces of jargon that help?
Tasteful jargon. So, for the most part, I tried really hard to eliminate as much jargon as I could. Now, in this talk, for example, I use complementarity, but I had a reason for it. What I try to do, Mike, is I think about who, for a lot of things that I try to speak to, I think about how would I explain this to a smart 8-year-old? And then I think about how do I have to condense this down? And often you can't even get to the level of jargon, you have to get to the higher ideas of what's behind it, like the big questions, the why. And then those are actually compelling reasons. Most people don't care about my day-to-day job, which is involving sitting there for hours, turning a little knob on the laser, trying to move a little beam a millionth of a meter to the left, right? Like, that's not so exciting. And that's not what excites me about what I do. It's these bigger pictures. And so trying to think about that audience, for me, an 8-year-old, that's something that's quite compelling. Now, I used to think that, okay, well, maybe, I'll think of an 8-year-old for this, and then maybe a smarter person for that, or maybe, somebody's 25, or maybe a physicist for different settings. It's actually turned out that even when I give talks to other physicists, I now go back and I think about how can I explain this to an 8-year-old. I give those talks to even people in my field, and they love it. It's fantastic. It's the most engaging things, because then I start thinking about, maybe I'll use a balloon to explain this as opposed to this complicated graph nobody cares about. And it's a different way to engage. So, my goal is smart 8-year-old. I don't always hit it, but that's at least what I strive for.
When you're talking to other people in either your own discipline or others, and their default is jargon to the point that they don't even know they're using jargon, how do you explain to them, how to be aware of that? Because in conversations I've had, it's just they seem to think that they're speaking on a regular level, and they've adapted the jargon into their regular vocabulary and don't even recognize it anymore.
So I have two things to say about that. The first is, the first is what I forgot what I was going to say. So I'll go to the second one. So this reminds me of the story of Richard Feynman. And Richard Feynman, he's like this Nobel laureate in physics, but he was known as one of the great teachers, and he had a very clear way of explaining things. And his solution, his target audience was always an undergrad lecture. It's like if he'd be talking to his colleagues about some of the most advanced, cutting-edge research, and he'd actually want to take that and explain it to an undergrad group. And there's this one famous problem he was working on. And he stopped and said, okay, I think we're at the point. I'm going to go and give an undergrad lecture next week on this. He came back really clear and said, I can't do it. It means we don't understand this. We've just been talking jargon to each other. We don't really know what we're saying. There's something here. And it's one of the things that contributed to him winning the Nobel Prize. So I think you can start not calling people on, but it's often, if you start simplifying your language and you start asking simple, penetrating questions, because often people use jargon as a shortcut, but we sometimes forget about all the assumptions that went behind that. If you can start hitting at those things, say, wait a minute, so how did that imply X? And start asking really basic questions, that forces people out of it, and it forces them back, and it kind of slows you down, and then you start catching things. Find me to do this to people a lot too. You go into a lab, you kind of dawdle in, and they start explaining the research, and you're like, no, wait a minute, I just have a really basic question about, just a simple theories. And you ask, a little question about this, and people get kind of irritated with it because you just kept asking these really basic questions. And then after asking that basic questions, you pull the rug out from underneath it and say, well, you had all these assumptions. Clearly this doesn't add up. And the research whole program would fall. Like the reason what they were doing. And it'd just be left going, what just happened? And I think it's this idea of clear thinking, or just really trying to get to the essence. And if you think about that, like, wait a minute, what's really going on here? Why? I keep asking why. That can help bring someone back. It's also age too. If someone's really old and they're stuck in their ways, it's very hard. Sometimes when people get set. But I think for most people, just asking why and really bringing up clarity, that's what I do.
Yeah, it seems like you spend a lot of time thinking about this and spending time giving talks to people. And yet you're also doing a lot of research in that. I'm wondering if you encounter any barriers within your discipline and the people that you're tackling and with your job as you take on this sort of communication role that's not really outlined in a lot of academic roles.
So, yes, I encounter a fair bit of resistance. So one thing is I don't sleep a lot. It's usually like I go to work, I come home from work, and I immediately begin working on this, and then 1 or 2 I'll go to bed, and then wake up, sort of rinse and repeat. And I'll do that for a while, and then take a little break. It's a lot of work. You get a lot of resistance. I can't tell you how many other physicists and professors who come up and told me, you're doing really great things, but you're wasting your time. Because this isn't what gets you academic promotions. This isn't why people hire you. A lot of, I don't know if I should be saying this because it's the peek behind the curtains how sausages are made. But the sausage making, so to speak. A lot of research institutes, it comes down to money, how much money you bring in, and that depends on how much you publish. And there's all these games you play. And if you're doing every moment that I'm spending doing this is something that I'm not doing to get a publication, which is therefore not bringing things in money, it's not bringing in prestige, it's not bringing these other things. And there's a lot of resistance to this, and I've told that. And that really discouraged me for like the first little bit. I stopped, I didn't do any. This is part of the reason I had these 2 separate tracks in my life and never shoved the 2 mixed. And then I got thinking about it and I realized I don't want to live my life that way. I really want to live in this intersection. And I don't want a job at a place that doesn't value that aspect. Because I don't think these people are going to be the forward-thinking or the real breakthroughs happen. I really think it's at this intersection. And so I don't want to work at a place like that, so I'm going to do the things that I feel are important, and sometimes it takes a lot of time. But I feel it's valuable, I believe in this type of stuff, I enjoy it. It makes me a better physicist, and I think a better person too. Like I can't put myself much deeper, so I'm going to keep